Word up. Nationwide hated. Nickel plate.
SaneQL or death? Yo, son, what are you going to choose? Yo, check it. This seminar is filmed at Carnegie Mellon University. Thanks a lot, Google.
All right, guys, welcome back to another seminar series. We're extremely excited today to have both Viktor Leis and Thomas Neumann presenting about the replacement for SaneQL. I don't even know where to begin with these guys. They're both professors in TU Munich, which is basically the database capital of Europe, if not the world. But let me go through quickly all their awards because they have many and it's worth discussing. So for Viktor, he won the 2024 VLDB Early Career Award, the 2014 ICD Best Paper Award, the 2018 Sigma Best Dissertation Award, and then 2019 Most Valued Rookie Database Professor in Database World Yearly's Faculty Rankings. For Thomas, it's even more prophetic. He won the 2014 VLDB Early Career Award, the 2021 VLDB Test of Time Award, the 2021 ICD 10-Year Influential Paper Award, the 2020 Gottfried Wilhelm Leibniz Award, which is the top award in Germany. And then he was ranked number 1 in the 2024 Database Digest Power Rankings. So, these guys are the best in if not Europe, the world. So we appreciate them being with us. And it's 10:30 in Europe. So we thank them for staying up late. Thomas, the floor is yours. Thank you for being here.
Yeah. Thanks for the introduction. So today, I'm sorry too fast. So today I want to talk about towards Sanity and query languages, because why we like query languages in general, of course, we're very fond of them, have many advantages. They also have problems, at least the way they are used today. And so first, in general, I should clarify the relational model that we all use for relational databases. This, of course, is a great idea. So relational model is absolutely great, has many great properties. And here, perhaps you know these papers here by Mike Stonebreaker and Andy Pablo. What goes around comes around. So this talks about that we should all use SaneQL. I would agree on the part that we should all use the relational model because this has many, many great properties. I'm not 100% convinced of SaneQL, and in the following I will talk about why. So now, first I should say, of course, there are good and bad parts in SaneQL. First we start with the good. So what is extremely good in SaneQL, of course, is the declarative query language. So we absolutely want this. This is a great feature. Other parts of SaneQL are a bit more difficult, but still okay. For example, we have multi-set semantics. So we have bags instead of just mathematical sets. We can have duplicates. And this, of course, required for reality. Makes everything more difficult, but we accept this. Also, the three-valued logic is always a pain, difficult, but we need this. So this is all parts that are fine. Now, what is not fine is the part below here. First, the syntax of SaneQL, this is really strange. Now, this was imagined in the beginning to be something like readable English or nearly readable English, so you can just read the query to know what's doing, but as I will show you later, it's absolutely not true. So this is just gives you an illusion for very simple cases. And then the extreme syntax constructs makes it very difficult to add new features. And also, there are no decent abstractions, and this is all very unpleasant. And perhaps more damning is the last part. Even though we know more or less what the syntax of SaneQL should be, but the semantic of SaneQL is often completely unclear. We don't know what it does. And also, if you compare different systems, you see that they behave differently. This is also extremely unpleasant because this shows you basically that we have a failure of the system. So we cannot use it in the way it was meant to be. Therefore, in the following, I will first start and give you a critique. So show what does not work well in SaneQL or what are problems of SaneQL. And then we will talk about fixes later. But we will first start with the problems. So one, of course, the syntax of SaneQL is also always a bit, has very arbitrary looking rules. For example, if you look at this common table expression example here, so we have 6 common table expression constructs and only one of them is correct. And even if you know the rules, you have to look very carefully and check each different line and see, okay, which one is correct and why is this wrong and why doesn't this work and so, yeah. And by the way, if you want to check yourself, I don't want to delay this in a lecture, I would ask my students to check. But here you see only version number 4 is correct. Everything else is wrong. And it's not so totally obvious why this is the case. I mean, of course, you can look it up, but it's so as humans, it's not so clear why. And then other problems we have, everything is done in this pseudo-English, which means we have tons of keywords for everything. So every construct that you have in the query language is expressed with keywords. And in the beginning, so SQL 92, we had 227 keywords, so it was already a problem. And now in SQL 23, we have 409 keywords, which is an insane number compared to the active vocabulary that most people use in their daily life. Now, with more or less, you can say if you have an English word, there's a pretty high chance that this is a keyword. On the other side, of course, not everything is a keyword. Yes, only some of them. This is a huge pain because we don't know what we can safely use and what we cannot use. Here, this is a quote from the SQLite documentation that says basically that the list of keywords is so long that nobody knows anything anyway, and therefore you should simply never use an English word as a name as a column or as a table. Because this is not good either. Or you could do other things. You could quote everything. This works, of course, but it's also painful to use. Then some database systems like Postgres go out of their way and try to allow you to use keywords, even though the SQL standard would say that you must not use this. But in many places, it accepts keywords if the grammar gives it this. But again, this leads to different behavior. Some systems accept the keyword, some don't. This is all terrible. Then the syntax in general is unfortunate. Like here's a classic join query, a really traditional join query, like we are joining 4 tables here with some filter conditions and joins. And now this looks perfectly harmless, this query. The problem is, of course, this query here is wrong. And this is wrong in a subtle way. No, it's not very subtle, actually, if you look carefully, but in the first glance, it's not obvious what's wrong. And I can tell you what's wrong. It's missing a join condition. So what we should do is we should have a join condition between customer and orders, but we didn't. So we forgot this. We can easily happen, but you don't get an error message. And for this particular query, even worse, you get an answer that looks plausible, but it's wrong. And this, of course, is very, very unpleasant. In fact, what we have decided to do in our systems, if you do this and we see you create a very large cross product, basically, if you give an error message and say either you write here cross join, or you can have a setting to disable this, but otherwise I refuse the query because probably it was a mistake. But this is not in the query language itself because the query language allows you to do this. It's also not very nice. So we want a query language to be intuitive and to be robust. It should not be easy to make mistakes that lead to completely wrong results. This is simply not a good behavior. So, and in general, if you look at the syntax, it has many unpleasant constructs. Some things you have to repeat for no obvious reasons. For instance, look at the query on top here. This is a group by query. So we are first joining a region and a nation, and then we are grouping. And so you see that we have to repeat the group by columns twice. So we have to put them in the group by, and we must put them in the select if you want to output them. As we have to write them twice. And this is, of course, not nice. Then some people try to fix this. For example, DuckDB. So they try to fix this, and they say, hey, let's just introduce this syntax that says group by all. So we don't have to write everything in the group by, but we put it in the select. Problem is, this is a super, super dangerous construct because now you can accidentally, while writing something in your select, you accidentally group by something that you didn't really want to group by. And then you get wrong results or unexpected results in the output. So group by all is dangerous, really dangerous, and this here has redundancy. This is not great. Or the other parts, because everything is done this English style thing. You see the syntax to compute the median value, basically. So you see percentile continuous query. And you just look at this. This is from a pure syntax perspective, super long construct. Many constructs that we have in SQL are extremely verbose. So a lot of things to write. And all of them have special syntax. I mean, writing a parser for SQL is really a pain because of these really strange things that you can write in some parts of your query. This is also not a good feature. And then finally, I mean, the original argument in favor of SQL was it's so easy to read. You just read and then you know what's going on. But if you think about this, it's not true at all. Like here you see an example queries that contains the usual constructs. So we have select, from, where, group by, having, order by. And you, of course, you as a human, you read it from top to bottom. Yeah, you start on top and then you just read it. And this is your query. But if you think about how is this query evaluated, and not only evaluated, also concerning visibility, like which parts of the query are available where. Yeah, you see that the syntax order has very little resemblance to what's actually going on. Because here you see the corresponding semantic order. Yeah? So we start with the from clause, which is somewhere in the middle here. So then we do the where. Now then perhaps also the join conditions first, and then the filter conditions. And then we do group by, and at this point we evaluate both the group by and now the aggregate from the select, but only the aggregate, of course. Yeah, so the aggregate from the select. And then we have an additional filter, also having clause, additional filter. Then we do the window query. We cannot filter after the window. Why not? This is the way it is. Okay, and then we do sort, and then we project. But you see this this not intuitive at all, and also not something you can easily ignore. Yeah, because sometimes it hurts you if you don't understand what's going on. Okay, so these are all very unpleasant properties here of SQL. Now, what can we do better? And so we have looked at ways to make it better, and I will tell you something now next that we already talked about at Cider, I think 2 years ago. But I should tell you already that while this is an improvement over SQL, this is not an ultimate fix. So this, what I talk about next, fixes some of this problem, in particular this very strange syntax, but it does not fix all of the problems. So because the other parts will be covered by Viktor. So I will only talk about the syntax problems that we have. So one thing that we said, okay, we want to have a query language that is both simple and expressive. Therefore, Viktor came up with his name here, simple and expressive query language, SaneQL. And this, at a first glance, looks a bit like the data frame APIs that you might know, but there are some differences here. First, it's a real query language. It's not tied to a programming language. You can send it as text to a database, and you can get answers. And also, it has other differences. I will talk about this a bit in a moment. But first, now, what is different and what is common with compared to SQL? First, like SQL, this is a declarative query language. Yeah, and it has multi-set semantics, three-valued logic, everything is before. Now, because in a way, it is like talking about relational algebra. So this is, in a way, a text representation for relational algebra. Now, what is very different from SQL is that we have a totally regular syntax. There are no keywords in there at all. Everything is regular. You can easily parse this. We have explicit semantic ordering, and actually we also have more high-level constructs than SQL. But even if you ignore this, just as a much more straightforward query language, much easier to process in all dimensions. And for this, we also have a prototype implementation that you can play with this if you want. And what our prototype does is it allows you to transpile to SaneQL to SQL. So you can just use it with any database out there, because you in the end construct SQL. The SQL is sometimes a bit long, but it doesn't matter for you as a user. So if you just as a backend. Okay, now how does this query language work? In abstract way, we are evaluating functions over relations. So here you would see a way like we could join two tables, but usually you will not want to use this syntax. Instead, we want to use a nice syntactic shorthand for this. Namely, you say we take a relation and then we apply a method which is implicitly a function call. Then we apply a method on this, and we say we have a table R, and then we join this with a table S, and then we have a join condition, and that's it. So here you see explicit all the joins, and also with this construct you cannot forget a join condition because you explicitly write it next to this. A bit like the explicit join syntax in SQL, but in this case much shorter, and also note that there's no fixed evaluation order. You can write them in any order that you want. Like you can have a construct like this. We have here a nation, then we reverse to a join, then we filter, then we do group by, then we could do window filter, whatever. We can apply them any order that we want. Also, we have other constructs here that to make your life nicer, like this function that you have can have keyword arguments. For example, if you look at this join here, you see that this has an optional argument that you can provide, namely the join type. In this case, we say we want a left outer join. And also you have not only single values, but also lists of values. Like here in when you do group by, you give a list of columns that we want to group by, and you can also assign a name to a attribute in a list. You see the aggregate function here is the result is called CNT. So this is a name that you assign to this. But again, a very regular syntax, and you can express everything with this without having to invent syntax for everything. In fact, the query language is more powerful than this. As you are not only can you do what you do within SQL, you can do even more high-level constructs. For example, here is something that you might not do every day, but this is basically a higher order function, so a function that takes another function as argument. Because what we are doing here is we are implementing a left semi-join. Just to show off here that this is possible. So we define a function that given to arbitrary tables and a join condition, we evaluate a left semi-join. And you see this has to do some constructs here, like we have to invent a new column name that is guaranteed to be unique. We use the scan swim function for this. Then we apply a number of operations, and in the end, we get out the result of a left semi-join. And now you can use this function just like a regular join that you had before inside your query. And this allows you really to decompose your query and have reusable parts, which you never have in SQL. Because in SQL, the only thing you can reuse is a view, but this is not a lot. The view has no arguments. In particular, has no arguments that are not just simple values. So therefore, everybody codes everything ad hoc. But I think it would be much better to do a composable part and reuse parts. Okay, so this SaneQL construct, so this data frame style has many advantages compared to the classic SQL. Yeah, so it's first it's much easier to learn because you don't have to remember evaluation order. It looks as if it would be an interpretive program. And note that in reality it's not. Yeah, it looks imperative, but it's not. So you can still reorder everything. It's a declarative query language, but it's easier for you as a human to understand, and also easier to debug because you can ask for every intermediate result, okay, what's the result? You can get decent error messages. And also, if you think about using this, it's much easier to implement compared to a SQL. If you would start writing a new SQL in a front end from scratch, you probably need several months for this. Yeah, the SaneQL interface you can probably write in a week. So this is much simpler. Also, we have a demo for this online. Yes, you can play with this. You can give it SaneQL queries, and it will execute this. Actually, what it will do internally, it will use the transpiler, which is available on GitHub, to translate everything to SQL, and then runs the SQL statement, and then you get back the answer. Okay, but as I said in the beginning, so this here, what I said so far, fixes the syntax problems that SQL has, but does not fix the other problems that SQL has. Okay, for the other problems now, Viktor will take over, and he will tell you what to do about it.
Okay, so yeah, as Thomas said, right, I mean, all these things might be, maybe you agree with them, right? But maybe some of you have been wondering, okay, maybe that's all true, or maybe it's not true, but it doesn't matter because SQL is I think Snowbreaker was calling it the intergalactic standard, so there's nothing we can do. But frankly, after we did all this SaneQL work and this analysis of SQL, we kind of came to realization that it didn't even touch kind of the biggest problem that SQL has, right? And so this is kind of what the second part of the talk will be about. As Thomas said, this second part is more work in progress, so there's no paper on yet. So hopefully we can have a discussion on that. So the main problem of SQL, this is what I'll be arguing, is that nothing is compatible with anything. So SQL claims to be a standard, but it's not really a standard. So this is really a very strange kind of standard. Because if you look at any particular implementation, you will see that it doesn't implement the full standard, right? That's the first point. Every implementation also intentionally deviates from the standard. So the extent to which it deviates from the standard depends on the system. So for example, Postgres, which we'll be talking about more, follows the standard more closely, but even Postgres deviates in some places, whereas the old school traditional vendors, they deviate like crazy. And the systems also not just have like deviations in where they behave differently, but they just come up with completely new stuff. So they have non-standard extensions. And as if that's not enough, right, then the standard, even though it's huge, nobody implements it. It actually also doesn't specify many really important things that you would really expect from any programming language to be in the standard. So, for example, implicit typecasting rules and other things. So we'll see some examples of that as well. Graphically, right, you could basically summarize the situations like that. In particular, if you compare the SQL standard with the commercial vendors, they really the overlap between the standard and any particular commercial system is not that huge. And then also all the major commercial vendors differ from each other to a huge extent. So trying to write a query that like really works in several systems is like really, really difficult. And we actually have a couple of examples here that are really just not meant to be kind of the biggest problems or the most interesting ones, but just a couple ones we came up in recent times. And they show some of the simply bizarre things that you will encounter if you try to run the same queries in different systems. So, for example, let's look at this very simple query, the first one. So what's wrong with it, okay? Now, the answer is, according to the SQL standard, nothing's wrong with it, right? So, well, you have some subquery in the from clause, right? So what? Everything should work. But if you run this in Microsoft SQL Server, it will tell you the following error messages, right? So you're not allowed to put an order by in the subquery, right? And there is some logic to this error. Actually, you could say, well, because the order by is kind of not really, it doesn't have any meaning there. But SQL Server is really the only system that insists on that, right? So if you imagine if you have some kind of query generator, then it might generate something like that, but the SQL Server would just refuse to run this query. So it's very paternalistic in a way. So it doesn't, it thinks it knows better. And by the way, it has many similar situations, similar behavior in other places as well, where it will really tell you this is not, you don't really mean this, right? Even though you maybe do. And by the way, this would be a very useful warning, but for SQL Server, this is an error. Okay, let's see what else we got. What's wrong with this query? Select star from, we're joining here with the two tables R and S, and we use a full outer join and some join condition. And the answer again is there's nothing wrong with this query except that Postgres doesn't support it. Right? And more generally, more specifically, PostgreSQL does support full outer joins, but it doesn't support them only with basically equi-join conditions. And here we have a less than instead of an equal, and then it just doesn't support that. And this is one of these exceptions, right? Generally, I said that Postgres is actually very standards compliant and also very orthogonal system as far as SQL systems go. But this is one of the exceptions where even Postgres kind of fails. And then the third example is a little more complicated and indeed very, very bizarre. And Thomas learned about it, I guess, pretty recently and changed Umbra that. So this query actually works in all the systems we tested, but in some systems such as BigQuery, it produces completely different results than what the standard says. And so specifically, actually, BigQuery breaks the standard, but computes what you would expect. So if you look at the select at the end, it's scanning S, right? So and S, as you see, is a common table expression with 2 rows. So what you would expect the query to return 2 rows. But actually, the SQL standard, for some very bizarre reason about the aggregate scoping, will tell you that this query is supposed to return only 1 row. Okay. Yeah. So these you have all these kind of very bizarre cases, and the point of this slide is that every system has them. Okay. It's not picking on these specific systems, but every system has that. And they are only some of them are documented, many are not. So how can you write complex queries that you can make sure that they work in many different systems? Basically, the answer is it's impossible. It's always a matter of luck. Now, what you could say is that who cares about these other systems? Okay, there hasn't like Postgres become basically the new standard. Okay. And indeed, Postgres is kind of, as I said, it's very orthogonal, right? It mostly follows the standard. So, and for that reason, many systems nowadays try to emulate the Postgres dialect and to some extent their semantics. The trouble is, well, again, right, you can very easily find examples where systems such as DuckDB and Umbra that claim to be or try to be Postgres compatible deviate from what Postgres does. So, for example, in this first example, the average of DuckDB, in contrast to Postgres and Umbra, will always make the type a double, right, rather than numeric. The second example with this round is kind of interesting because Postgres has this very strange numeric data type where where the number of digits after the comma basically is not static but dynamic, and so each value basically encodes how many digits after the comma it has, and that's very different from virtually all systems. And this has implications, as you see here, right? That the Umbra type of the round call is kind of has more digits than the Postgres one. I mean, there's a good reason why Umbra does it that way, but it's clearly a deviation. Then Postgres has this strange construct where you can have basically a relation without any row and without any attribute. So just select, and this just works. And DuckDB doesn't do it. Right? Postgres also has this interesting concept of an infinite timestamp, so plus infinity in time and also minus infinity in time, which you can imagine sometimes may be useful, but it's actually not non-trivial to implement. So Umbra, for instance, right now doesn't implement it right now. Postgres also has these these strange numerics, and so you can and indeed arbitrary precision numerics. So you can create very large numbers, which most systems do not support. Right, and we're now, by the way, I'm not only comparing systems that claim to be compatible with Postgres. Okay, so if we kind of graphically summarize the situation here, it looks a little bit better than what we had with the commercial vendors, but still, right, even Postgres is not fully standards compliant, and even these systems like DuckDB and Umbra that try or claim to be compatible are not fully compatible. And indeed, DuckDB is kind of infamous here, right? So this is why we have this little mouth of the duck here, because they've been adding all kinds of crazy syntax extension, which might be kind of useful in some situations, but they kind of fragment the space more and more. Right? So this is it's not clear if that's a good trend. Okay, so yeah, but you could say, come on, you just came up with like very obscure cases. Who cares about all these kind of obscure cases? Incompatibility, most queries will do similar things, maybe. Yeah. But first of all, I mean, one could produce a presentation with hundreds of these cases. So it's not like this is an exhaustive list of anything, but this list will never end, basically. And what I would also like to argue is that these differences really matter, right? So that you get different results, right? And because obviously, let's say, depending on the numeric type you have, you might do other calculations based on that, and then you convert it to a string or whatever. So you really get different results in queries. You get so one anecdote, by the way, is that the TPCH standard, because of all these numeric problems that SQL has and lack of a clear type semantic, they just tell you that the results that you have to produce have to be close enough by 1%. Right? So this is all you can basically say in SQL, which is very bizarre if you think about a programming language perspective. So these problems really matter, right? Because SQL queries are also not just written by humans, right, who can deal with these kind of bizarre error messages that we saw, but they are nowadays most commonly generated by machines or by code generators. And so basically SQL is a programming language, and you would expect it to have some kind of semantics that you can understand. So after all, I mean, database systems, they are foundational technology, right? All kinds of high-level things are built on top of that. And so I think we should really think hard how to improve the situation. This is not a good world we're living in. And specifically, if you think about the kind of things that are very, very hard because of this lack of standardized semantics, yeah, you can come up with a very long list of great stuff, right? So here's a couple of things that we came up with. So, for example, federated databases, right? Very old idea that you have several different databases, and then you just write one query that queries them all, right? And this is extremely hard. It's extremely hard. Many people have tried, and typically it's kind of a best effort solution, and it doesn't never quite guarantees that it's both efficient and correct. So you kind of have to pick probably. And another thing that never really took off is things like hardware acceleration for database systems. And I believe one reason is that nobody knows, right, for which kind of semantics you want to put into hardware, because which dialect do you want to implement. So the market is like super fragmented because everybody has their own semantics, and the semantics is also not very clear. It's encoded in a million lines of code. So what do you implement as a hardware vendor? It's not clear. Maybe one of the saddest thing for me personally is also there's this great trend of these composable data systems like Parquet, Data Fusion, Calcite. And on paper, it's amazing, right? You just take these components, plug them together, and then you have a database system. The trouble is, if you look carefully, again, you run into all of these minor semantical deviations, right? So specifically, they have different type systems, okay? So let's say you want to support these infinite plus infinity timestamp, okay? And you implement that in Calcite. Well, then you also have to implement all these extensions, data fusion, or all these operations on these strange timestamp. And then you will also need to change Parquet because maybe Parquet it cannot store these strange timestamps, right? And so right now, this is like a huge hassle. And each of these projects then tries to be extendable to some extent, but I think this will in the end never work. The complexity will just kill you if you don't standardize on some whatever semantics you want. A similar point is Microsoft Insider was presenting this query optimization as a service idea or project. Again, this is an amazing idea, but how can you do that if you don't quite know the semantics? And how can this work across different systems? So at MIT, there's a project like that where you somehow declaratively decide or specify kind of workloads, and then this project system will decide which database systems you work best for your workload. And again, right, this somehow assumes, similar to federated databases, that you can somehow move queries around different systems, which is like very, very difficult. Maybe one of the biggest thing that a clear semantics could have, or maybe one of the biggest effects that a clear semantics could have, is that you could get real competition between vendors. Because right now you have these islands where once a customer adopts some certain product, they can never get out of that, and they are trapped. So I still recall a senior manager at one of the big commercial vendors saying that the most valuable asset that this database company has is its test suite. Because if somebody else had that test suite, right, you could just, with all the bizarre semantics, whatever they implement, then they could implement that as well, and then they could actually steal the customers. But as long as nobody has that, and as long as the semantic islands are as they are, you don't really have a lot of competition is severely hindered. And yeah, and you could also once you have a clear semantics, you could use like formal methods. You could prove stuff about query optimization and transformations and so on. This is will help tremendously. Specifically, right, not just at the relational algebra level, but also about really the full semantics, including nulls, including type propagation, all these things. And these are things that often lead to a lot of bugs. So there's all these amazing things that we can't have right now. So how do we get to a world where these things would be possible, or at least much easier? Okay. And so one superficially very nice idea is basically what the Substrate project is doing, right? So some of you may be familiar with it, and this comes exactly out of this composable data systems world, because I guess it's kind of natural once they build all these components. At some point you realize, well, you need somehow to ship relational algebra around, and so they came up with this cross language serialization for relational algebra, and it seems very promising on first look. But the trouble again is somehow they try to be kind of very generic. So they support or they want to support at least many different systems with different dialects. And so Substrate itself needs to be to handle all these different cases a superset of all possible semantics. And then they define kind of the syntax, but they don't actually tell, okay, well, which specific semantics should anyone support. And so you have this blow up of complexity in a way. I mean, there's other things you could discuss. So, for example, somehow they also couldn't decide, because for different use cases, they had different requirements. Kind of, should this be a logical plan for or a format for logical query plans or physical query plans? And so, yeah, somehow this is not quite what we want. Although it seems like a good idea at first glance, right? So maybe some of you are familiar with LVM IR, and so and some of you may even be aware with MLIR. And so a substrate is something like MLIR and not LVMIR. So yeah, Substrate is not the solution. So what do we need? So our idea here is that what we need is something like SaneIR. Okay, and by that we mean a well-defined semantics for relational operators. But this is not enough, but also for all the expression stuff. So scalar expressions, built-in functions, data types, how the implicit casting rules work, how errors behave. I mean, overflows, that kind of things, runtime errors. And ideally, this would initially be kind of a really formal specification. It would, of course, be extremely useful to have a reference implementation. And then you have kind of a standardized several standardized formats of how you move this thing around, right? So maybe there might be some in-memory representation and maybe some JSON representation, right? And so Substrate focuses more kind of on the last point, but we kind of argue that the main point is actually to coming up to with the former points, right? Or the specification in particular. Okay, so how do we get there? Okay, so maybe you agree, okay, it would be great to have that, but isn't that kind of wishful thinking? How do we get to this island of sanity, right? And so I think initially, really, the core, of course, is you need interoperability with Postgres. As we discussed, this has become kind of the lingua franca nowadays, the most common dialect. And so our idea is that if we once we have defined kind of this SaneIR, we need to build this little bridge, right, towards this Sanity by building a transpiler from a subset of PostgreSQL style SQL to the SaneIR, okay? And then once you are in this SaneIR, you can then also transpile to different systems. So initially, you may start with a couple of these Postgres compatible systems like Postgres itself, and maybe DuckDB and Umbra. And the nice thing about this is that kind of it gives you a kind of a smoother path into this world. But of course, the longer term vision is that people implement SaneIR directly and don't have to deal with SQL anymore. So they can use then our SQL front end. And then other systems like query engines, they only need to think about SaneIR and don't have to think about any of the other front end languages at all. Right? I mean, and another benefit actually is that it could also lead to more innovation in the kind of surface level query language part, right? So SaneQL and other query languages that I guess you'll hear more about in this seminar in later weeks. They can just hopefully plug in kind of in this SaneIR that will make it much easier to implement new query languages. And so this is kind of obviously we don't know if this will work, but this is kind of one way we kind of envision that such a project could have real world impact. And so it would be kind of these three steps, right? In the first step, it's kind of only a transpiler, and so in the second part, then these composable data systems, which I think really are in need of something like SaneIR, they could adopt it. And once then these composable data systems become kind of widespread, hopefully the commercial vendors will be forced to adopt that as well, right? And this could be analogous to what happened with data lakes and Parquet and so on, which is pretty amazing that basically now all commercial column stores have been basically forced by a customer to implement that stuff, right? Even though, let's say 10 years ago, people would not have believed that these commercial vendors would do that, right? Okay, so as I said kind of earlier, this is kind of still work in progress. We're still pretty early, so there's many open questions. We don't know if this will actually work out and how exactly the SaneIR will look like. So here's a couple of questions that we've been thinking about, but we don't really have full answers here. So how similar should the semantics be to PostgreSQL? So initially it was probably pretty important to be relatively close so that many things are kind of it's easy to transpile to SQL and or to Postgres SQL. Another question is, okay, can we support other systems that are not Postgres compatible, and how efficient is that transpilation, and which system do we want to support? Because you can, of course, through this transpilation, introduce many new rewrites that will solve many or allow many constructs, and so yeah, how far can we push that? How big can we make this island of sanity? Yeah, how large can we make this? Okay. And then finally, a big issue is how do you define error behavior without kind of preventing very important optimizations that we kind of query optimization opportunities that we have in SQL. So yeah, these are some of the questions that we're thinking about. So let me kind of conclude, right? So I think the one important point is that the relational model is great, so we don't want to kind of destroy that. And historically, or let's say in the last 40 years or so, the relational model and the success of relational model was very tightly linked with the success of SQL. But I think this is the success of the relational model is really despite SQL as a language. It's a terrible language in hindsight with all we knew today. And so the syntax is really terrible, makes it hard to learn, debug, generate, to implement. And no two systems are compatible. And this lack of compatibility, I think this is not just kind of minor convenience, but it really hinders innovation in the data world. Many great ideas, many great startups don't quite work because of this, even though conceptually they should work, but they don't. And if we had this well-defined relational IR, I think we would be in a much better world. Yeah, thank you.
Awesome. I will clap on behalf of everyone. We have, a lot of time for questions. So if anybody has a question, feel free to unmute yourself and fire away. You want to unmute yourself instead of doing a chat.
Yeah, Thomas, Viktor, awesome talk as always. Obviously, the work that you presented at CIDR 2 years ago with the initial SaneIR was very influential. Google did the pipe syntax, which they disclosed last year. There are lots of proposals. You mentioned PRQL for folks trying to come up with a new type of SQL. And this sort of feels like the early days when there was SQL and Quell, and then later on QBE. The community never got together to say, at least even on the academic side, as to let's group together to make one. So I was wondering if there is any thinking from your side to see whether you could band together. Because ultimately, the problem with SQL, you guys mentioned very articulately all the key issues with SQL, but many of these over time people have tried to fix, like parameterized views. Systems support that, but SQL does not have that in the standard. And some of these are fights in the standards because, vendor A doesn't want that because their product doesn't have it. So for this to stand any chance, which is obviously a great idea, I was wondering if there was this broader thinking of lessons to be learned from past attempts to do this, to make this feasible, because it would obviously be awesome if we lived in a saner query language world.
Yeah, so maybe I'll start, and maybe Thomas can add something that I'm missing. So in my mind, and this is how we've been thinking initially, right, with the original Cider paper, right? How do we make a better query language? But in some respects, you run into this risk of saying, well, there's 50 incompatible languages, and the solution is to compare is to propose the 51st, right? And then everybody has slightly different opinions about that stuff, right? And so somehow I think this is almost impossible to get consensus, right? And I guess you'll see that also in the seminar, right? People have all kinds of very strong and different opinions on what how the language should look like. And so somehow we got to the second phase to saying, well, maybe we shouldn't focus on that initially. So all these criticisms that we have in the beginning, I think they are true, but maybe the much bigger problem is actually the semantic issue that was talking about in the second part. And if we address that, then that would also enable new innovation at the surface level part. Right? So this is why we kind of shifted, because yeah, you're absolutely right. Many people have tried. Somehow it never went anywhere. So I think that's why my idea is to focus more on the semantic part.
That makes
Yeah, if I can add something. So first, I agree, of course, with Victor, and I think and I also think this is a harder thing. I mean, agreeing on a query syntax, this already, of course, people have different opinions, but perhaps you can find something. But agreeing on what should the behavior of a numeric data type is, this is much more difficult actually. But we have to do this, yeah, because if you don't even know how the basic types behave, how can we define what a query is supposed to do? Yeah, and therefore I think we need this, and we need this in a way that is not just in read the code. This is my reference implementation. We need a specification in something that is really, really like a formal description. If you look at what programming languages do, they usually say what the result should be precisely. Yeah, and we have to do something like this for our query language too, I believe.
Yeah, that makes sense. Thank you.
All right, if everybody has a question, unmute yourself and go for it.
Hey, can you guys hear me?
Yep.
First of all, thanks for the opportunity to give me to get allow me to ask questions. I have a couple of questions. My first question is, so Victor mentioned about IRs. So SQLite does internally have a bytecode engine, and it does it does essentially an IR form. So what do you guys think about that?
I'm not sure if I got the first one. Who has a IR?
Yes, a SQLite. It uses a bytecode
SQLite.
engine.
Yes. Okay.
Yes, because it uses a bytecode engine to execute the query. So it does have its problems because it's not parallelizable. So what do you guys think about their approach?
But many systems have an internal representation of a query. It's not only SQLite. Like even if you look at MongoDB or something like this, they also all have their own textual representation for a virtual machine. So this is a common approach. The problem is that everybody has a different behavior. So like a query in one query engine gives a different result from another engine. And I think what we have to do is we have to say this is the correct behavior. because otherwise you will always have you cannot implement a non-trivial application that runs on multiple databases basically without a heroic effort to port every single query to every single system.
Got it. Okay, so it's more about which should be used as a standard. So along the same lines, SQLite has a very good gist suite. So it just I think it just all of the operations on Postgres, MySQL, and SQLite. So it compares the results for all of them. So why not we just use SQLite standard as the correct one? Because it already is comparing against Postgres and MySQL.
SQLite is also strange. Yeah, so they have different. What was the problem with SQLite? I think SQLite, the problem with SQLite is that everything is duck type. So they have no static typing. And so the type is associated with each individual value. So which means each value can be different. Even if you have a case statement, yeah, different branches of a case can produce a different data type. I mean, this is insane. Yeah, and also non-standard compliant, by the way. Yeah, so standard doesn't allow this. But this basically means you cannot say SQLite is the right thing. I mean, we usually say Postgres is the right thing because most of the time they do the right thing, but sometimes also they don't. So they are pretty good, but sometimes they also do stupid things. And I believe in the end, you cannot simply say this system is right. You must look carefully and then decide this should be the correct behavior. Of course, you will try to choose something that most systems do anyway, but probably all systems have to change at least in some aspect.
Got it. All right. Thank you.
Chris, you want to go for it?
So you mentioned Parquet as like the common format for a lot of like OLAP systems. And like Aurora, Socrates, PolarDB also like make a cut at like the logging and storage layer. Are there advantages to building the IR at the query layer instead of building it like down at the data or storage layer? Like instead of like for federated queries, like it's important to like break that query across like have it like spread to different databases instead of having them be able to read a common format?
Well, think about a pushdown. Maybe even if you don't want to execute the full query somewhere in the storage layer, maybe you want to push down some where condition, right? And there, again, you're in this world of what exactly is the semantics of your where condition, right? And so I don't think you can kind of separate the storage layer from the rest, right? Well, other than you saying, okay, storage layer is just a byte array, but then you can't even push down where condition. Does that make sense?
I don't buy that argument. I could see a world where the semantics, if you have standardized on the storage layer, then I could see a world where you opt into the semantics of the query layer based on the system that you're having run it. There's no need for pushdown if the semantics of the query layer and everything's got access to it. Obviously, that's like not going to work all the time, but it's not crazy.
But
unfortunately, this will not work. So even if you think about Parquet, like Parquet has this concept of min-max filters. Yeah, you can for every block you can say what is the smallest and largest value, which is important for pruning, of course. Yeah. Problem is systems disagree. Like for example, how do you order? If you think Postgres orders not a number value in doubles behind behind plus infinity, so larger than everything else. Yeah, but not all systems do like this. So even on the very basic level. People disagree. So they don't even agree what the minimum and the maximum of a set of values is. But this is important for the storage layer because you need it for pruning blocks. And therefore, I think what you want, and everybody wants, is you have to define data types and their correct semantics, their correct behavior. And then you can use this in the whole stack. So in the storage layer, query layer, everywhere. But so far, people don't agree even on these basic things.
Isn't that a binding between like Postgres and Parquet? I'm sorry, I'm still not understanding why. If I have this common format, like, don't I still have to teach it Parquet?
The
If
thing is, when you build the Parquet file, the program who writes the Parquet file has to remember what is the largest and the smallest value in each row group, so in each block of values. You materialize it into the Parquet file. And but the problem is, does this agree with your query semantic? Yeah, because if the semantic of the one who wrote the file and the one who reads it agrees, then everything's great, of course. But if they don't, then you cannot use this bounds or pruning. Yeah, so you have to read everything.
So basically, sometimes your query are just wrong, and you don't know why.
Yes.
or it can't use the storage file properly because it was trying to use some different semantics for the type. It sounds like getting the type semantics right is really, really very important. Yeah.
Yeah.
Well, I guess do you still have a problem lurking in the how the data are stored underneath? Like, do you still have problems reading Parquet files even if everyone adopts SaneQL?
You mean our query language? No, I was saying, as I said, so saying our SaneQL.
The IR.
The IR. Yeah. So if we would have a common IR, which basically means we define what is the correct behavior for every data type should be, and then everybody should, or this should affect everything from a storage layer to a query layer. So this would help everybody.
I see. So they have to figure it out once, and then it's in the IR.
Yeah.
And then
Yeah.
So just as example, CalSat look at CalSat documentation. They have a different type system than your data fusion, and a different one than Parquet. I mean, how can this work? Just on a fundamental level, right? This is like, yeah, it cannot work, right? It can only work mostly, but not always.
Is it a smaller, more tractable problem if you try to only solve this at the type and storage layer? Or is that just sort of a waste of time? Like, I get that your IR, your language is good and wonderful, but would it help? Is it a step forward to even just get the standard type system, right? The fact that like Postgres has different types from MySQL has different types from Oracle has different types from CalSite has different types from all this stuff. This is just crazy to me. Like maybe only like how much do you get if you only standardize the types?
This is not only, this is the hardest part. Because if you look at people, so different systems, all of them agree what an inner join is, and most of them also agree what an outer join is. So the differences do occur exactly in the type system and the functions defined on types. As to the relational algebra, there's more or less consensus, not 100%, but more or less consensus on how systems should behave. The types are the hard problem.
Thank you. All right. Any other questions?
I have one.
Go for it.
Hey, Thomas, Victor, thanks a lot for your talk. I'm currently implementing your old paper, unnesting arbitrary correlated subqueries. And firstly, it got me thinking that like SQL claims to be an imperative language, but frequently allows very declarative logic to be expressed by developers, often contrary to their own interest, like leading to like very slow correlated subqueries. I was wondering if you are also doing the same thing or planning to do the same thing in the IR, like basically rewriting, let's say, a lateral correlated join to a more like a traditional join that is supported by like standard relational algebra and by all other databases, which I'm sure not all support this kind of join.
In fact, so the existing SaneQL transpiler supports parameterized functions, which immediately gives you the same as a correlated subquery. Because if you think about this, this is like a correlated subquery, and then this will be unnested afterwards, so that it goes away. And then you have, so this is not different from the SQL. The syntax is different, but the problems are the same. You still need unnesting logic. By the way, if you're implementing my old paper, I can warmly recommend you a new unnesting paper that will appear in 2 weeks, I believe, at the German Database Conference. So this fixes some of the some limitations of the original paper.
Great. What was the name of the conference?
BTW, so the German database conference.
Oh, okay.
I'll post a link in chat. It's assigned reading in my course for Wednesday. Here, it's in the chat. Boom. All right. Somebody had a question before they left. I guess this is mostly for Thomas and the SaneQL stuff. They wanted to know your opinion about the other SQL replacements they're having, speaking this semester, in particular, like EdgeQL. But there's PRQL, there's other ones. Like, how do you guys? I mean, I understand that you want to have the same all go to SaneIR, and that's the common interface. But like, are there other aspects of things like EdgeQL that you like or dislike, and you think SaneQL does better?
To be honest, I'm not sure if I know by heart precisely what this one is, because I sometimes mess up the names. But I've looked at several of alternative proposals, and I mean, this is now, I must say, my personal opinion. No, Viktor doesn't think exactly like me, but I think that they are not ambitious enough. Because if you develop a new query language, you should not just have a nicer syntax. You should have really more functionality. In particular, I want to have higher order functions. So I want to be able to really write reusable components of a query that I can parameterize with comparisons, expressions, and this kind of stuff. It's not just that we want to improve. At least I think so. We should not just improve the syntax of SQL. We should really bring it into the world of a programming language, a real programming language with reusable component modules and all these things.
Okay, awesome. All right.
Is there time for one more question?
If it's a quick question, it's late for them. It's almost midnight.
I wanted to ask if there were possible issues that you were anticipating with transpilation. So you were talking about how you could unify the PostgreSQL and other SQL dialects to all become SaneQL. But what I'm thinking is, with all the discussion with type systems varying between different systems, if there might be some differences that could be irreconcilable, or I guess only reconcilable with some loss of information.
Oh, yes. Unfortunately, we also thought about this. Some things are really, really difficult to lower. In fact, we talked about, nothing is implemented, yeah. But we talked about that we might eventually even have to, if we want to transpile to Postgres, provide a custom module for Postgres that adds this, in some cases, semantics that we want, and so that you can get the behavior. But indeed, it's really difficult. Yeah. First, defining how the behavior should be is hard, but then getting systems to agree on this is even harder. Yeah. So then, yes, this won't be easy.
Yeah, it could be that for some systems we can do that reasonably efficiently, and for some systems inefficiently with crazy rewrites, and for other systems not at all. And that's possible.